Dan Olds here. I'm on stop 3 of my massive 4,500-mile HPC road trip, and I'm here in the library of NCAR. And
I'm Rich Loft. I'm the Director of Technology Development in the Computing Lab here at NCAR.
Very lucky we found you here. What a coincidence. What a great coincidence.
Yeah. It's where I work, so it's not that big of a coincidence.
Guess not.
Yeah.
But tell me a little bit about the mission here.
Well, as the name says, NCAR is the National Center for Atmospheric Research, so we study the atmosphere and more recently the entire Earth system, which includes the ocean, sea ice, land surface, everything that operates the climate system of the planet. And all of that stuff is a mixture of observation, theory, and computation, because the system is complex, nonlinear, and very dynamic. The only way to really forecast or simulate such a system is with supercomputers. And those supercomputers, when we started to develop machines like that in the 1950s, one of the first applications was meteorology, and that's stayed true for the ensuing 70 years, basically.
And even today you're doing meteorology? As in, when you say meteorology, I'm thinking of weather forecasting.
Yeah, improving weather forecasts, extending the time in advance that we can accurately predict the weather.
Reducing the area for which you can give a specific forecast as well.
Being more accurate, resolving structures. So if you think about a hurricane, a great deal of the damage potential and action of a hurricane is around the eye. The eye itself is only ordered tens of kilometers across. So if you can't resolve the eye, you can't get the winds right at the core of the hurricane. So those are the winds that tear the roof off of your house, right? So we need to have powerful computers to capture those kind of dynamical effects and scales.
And you have a pretty powerful computer in Wyoming, where we just visited at the Wyoming Supercomputer Center.
Yeah, we built that facility in 2012. The machine that's currently up there that we call Cheyenne, after the capital of Wyoming, is about 5.4 petaflops of Intel Xeon Broadwell V4 Xeons, and there's about 4,100 nodes in that machine of dual-socketed Xeons, and it's interconnected with EDR, so it's 200 gigabits per second.
Gotta like that.
Yes, it's nothing like getting good bandwidth in between the system.
And low latency as well.
Yeah, so all that stuff is good.
Using any accelerators in that system? GPUs, FPGAs, anything like that?
No, there's no accelerators in Cheyenne. We do have a system that we've just deployed recently, which is an analysis system primarily. So it's an adjunct to the main computer, and it's called Casper.
Okay.
And Casper is got a couple nodes. I think it has 24 V100s in it.
Okay.
So NVIDIA V100 GPUs is the latest generation, the ones that have 32 gigabytes of memory on board, and we have 2 that are 8-way NV-linked and 2 that are 4-way NV-linked.
Intel-based or power-based?
Those are Intel based on the CPU side.
Okay.
So they have Skylakes.
Sure.
As dual Skylakes as the front ends, and that the interconnect between CPU and GPU is PCIe. And I think that if I could just interject, I
Sure.
think I misspoke when I said EDR is 200 gigabits per second. It's 100 gigabits per second. I'm living in...
You're dreaming.
I'm living in
looking-
HDR space. 'Cause we're about to go to HDR, so I've just moved all my pointers forward one generation.
You're going to go to HDR on Cheyenne? Or is this for the...
No, but the next computer...
The next system.
Will likely have the HDR,
Yeah.
HDR bandwidths. So, yeah, I just was thinking about that while I was talking.
That kind of hit me wrong too, but I
Yeah.
decided let's just let him go.
Yeah, let him go. Well, you know,
Well, we've got it
you
corrected.
can either edit that out or you can just
We'll
have
leave
me
this
apologize.
in. That's fine.
Yeah, that's fine.
I know a bunch of people at Mellanox. They'll be fine with this.
I'm always thinking about things one generation ahead of where we are.
Well, that's where you're
I'm already
supposed to be.
living in HDR land at the moment.
Well, you know, that launches us onto a different topic too.
Yeah.
Where do you see HPC going?
Well,
That's a very broad question, I know. Answer it however
yeah,
you
and
like.
it's very tempting to say something impolite about that. Yeah, I will say that for our applications, you know, which are historically essentially solving partial differential equations with some physics forcing. I mean, at a very high level, it's mostly fluid flow equations with physics forcing. And the physics is all driven by solar energy and the thermodynamics of water vapor. And that, okay, there's the...
Sort of just laying it out basically.
I mean, yeah. I mean, if you were a physicist, you'd say, well, you know, it's okay, but it's not, you know, you know, colliding black holes or anything. So...
It keeps a guy busy though.
Well, you could argue that more people are affected by the weather than are affected by
the
colliding
collision
black
of,
holes.
yeah, absolutely.
You know, so from that societal relevance point of view, very high. So the thing that we're seeing is that our ability to push the resolution and push the throughput rate that we need in order to do the things that we want to do in terms of predicting and understanding the Earth system are starting to play out with the technology that we're using. So what I mean by that is that everybody sort of knows the cores aren't getting any faster. We're getting more of them, but they're not getting any faster. And so from that perspective, you can weak scale or increase the resolution of the model, but the throughput drops. And so if you want to talk about throughput in this business, you usually talk about the number of model days that you can simulate per wall clock day of computer time. And so that's sort of a measure of how much, you know, if you have to simulate 100 years into the future, you know, you want to do that in something quite a bit less than 100 years of computer time, right?
That would be optimal, yes.
Yeah, so that's throughput. And that requires kind of strong scaling. And so the technology has really been providing us with strong scaling. And that applies, you know, to GPUs and CPUs alike. I mean, we can get a little bit of speed up that way, but not sort of the dramatic things. So I think that one of the more interesting ways of getting around these problems that's been coming along, and lots of people are looking at, is machine learning.
Yes.
So why is machine learning somehow, you know, maybe helpful in this area? The answer to that is that there are at least some kinds of problems, I think, where we can not calculate what we need to calculate in the traditional way with human-crafted parameterizations or heuristics that are quite often very complex pieces of code that have lots of branches in them, that have a lot of things that frankly aren't physics in the proper sense of the term. They're distillation of observations. You know, somebody measured something about a cloud, they got a curve, and then they fit a line through that curve and then fed that into the model. Well, you can use machine learning to fit the model to the data as well. And
Much more accurately, I would imagine.
well, you know, there's accuracy, but there's also this idea that once you have trained a machine learning thing to actually emulate that process, the inference to produce an answer is much quicker than these pieces of code that you would use. So there are a couple examples there where we think you can substitute out expensive pieces of code with perfectly good machine learning.
In a neural network and
A neural network or some other machine learning algorithm. Machine learning is not just neural networks. There's a lot of other golf clubs in the machine learning bag. And I always think of that as sort of like you use the right tool for the right job. But
Yeah.
let's say it's some kind of neural network. Fine. So we put that in there, we infer something, and maybe we increase the speed of that by a factor of 100. You know, Amdahl's law then applies, and the things you've not turned over to the machine learning algorithm are now the dominant parts of the thing. So we have to go through this process, I think, of learning how to mix the physics we know and the physics that we can just train a neural network to emulate, so that we produce a model that's somehow substantially faster than what we're trying to do.
and better at predicting.
Right.
As well.
So, you know, it would be hopefully faster and better. That's a good quadrant to be in.
Yeah.
You know, slower and worse is not as interesting as faster and better. So, you know, in that structure of things, that's the quadrant you want to land in. And if we can get that, and we can just stop explicitly calculating things with these heuristic things, we might get a benefit. You know, and the reason I'm saying words like might and stuff is this is an area of active research, and it's not just going on at NCAR. There, as far as I can tell, just about every peer center or laboratory that's devoted to meteorology or climate or oceanography, everybody is looking at this and trying to figure out what the magic trick is to get this.
If there is a magic trick.
Yeah, and then there are other, so there's some interesting things where in certain conditions where you are just concerned with predicting one thing. You know? So instead of trying to get all the weather over North America right, you just want to know, is there going to be a heat wave in the East Coast of the United States or something like that? In some of those cases, you can. It appears that you can use machine learning to take observations in the history, let's say, of sea surface temperatures in the Pacific, and you can predict that one thing pretty well, maybe, and a lot cheaper than actually running an explicit model. So, you know, there are a couple of these kind of examples too, where if you're just looking at something that happens to be correlated in the system, you can cut out the modeling business entirely and just look for that correlation with the machine learning. So there's some really, you know, and that's sort of like saving yourself millions of dollars of computing hardware, because you know, these kind of things you can run on a relatively inexpensive system because you're not, again, trying to solve everything. You're just looking for one aspect. So there's a number of ways to get around this problem, and a lot of them seem to go through that particular approach.
And it's an awful lot of data that you have to analyze and correlate to get there, but once you have those correlations done.
Yeah, well, it's a different kind of HPC that's very data intensive. So then everything comes down to how fast can you feed training data through devices that are trying to capture these patterns, and then how do you feed that into a model in such a way that you don't cause the model to have a problem with what you give it. So, you know, neural nets are great for giving you a rough answer, but they sometimes don't respect things that we know don't make that are physical law. Like, let's say you have a neural net that's trying to predict water vapor, and it'll get a negative value. Well, negative water vapor concentration has no meaning.
Yeah.
That's like less than dry. Right? There is no anti-water vapor. So
I've been some places in Arizona that are like that, but I know what you mean.
Well, I would say that they'd be approaching zero, but they're
Yes,
not actually.
not less than zero.
Yeah, nobody's. I suppose there is anti-water, but it's not what we're talking about. So that when you feed those things into mathematical formula for thermodynamic purposes or something, it can drive them crazy, and you actually get a error or a seg fault because it's sent it off to a lookup table that
Just
is
doesn't.
out of bounds,
Yeah.
and things like that. So you have to be really careful about how you treat things like that with these. You can't just slap machine learning algorithms
No.
into these modeling systems.
And cleaning your data is hugely important going
Cleaning
into
the
that
data
stuff.
and then looking at the output of the neural net and perhaps correcting it or adjusting it so that it stays physical. And this is all stuff that people are basically learning by stubbing their toes and making mistakes and stuff like that. So, but it's really exciting because at the start of my career, I rode in on the rising tide of parallel computing. And, so parallel computing was going to be this thing that dramatically sped up our models.
What were the first systems you worked on?
Well, the first parallel computer that I worked on was the Thinking Machines
Okay.
CM2,
Okay.
which was massively parallel. It is basically a great big GPU, if you think about it in that sense. It was a SIMD. It was basically a SIMD machine. So that's where I cut my teeth on parallel computing. But the point is that in a way, parallel computing is now, in these kind of problems, is starting to play out. And so now I kind of see machine learning as one of the ways that we're going to figure out how to keep modeling beyond the impetus that parallel computing has given us. Either that or we're going to introduce some kind of device that you can clock at a terahertz, right? Which I haven't seen on anybody's roadmap.
New.
So without something sort of clocked super fast, so that the throughput goes way up, it's going to get harder and harder.
I mean, we're not going to get a lot more benefit from shrink either.
Yeah.
I mean,
yeah.
I think I might be alone in this, but I think we're going to have real trouble shrinking today's sophisticated processors down to 7 nanometers.
Yeah, and again, shrinking will just allow us to put more cores,
Which are not going to be any faster.
Yeah, and so having more cores doesn't actually help me
No.
or the people trying to solve these problems in terms of getting the throughput.
More of an enterprise thing.
Yeah.
And I'm not sure it helps them all that much once you get out past, 24, 28.
Well, I imagine there are apps that will that will benefit from this kind of weak scaling thing. It's just that things that require you to integrate at a certain speed of simulation rate or throughput rate, those things that are throughput driven are not going to necessarily benefit from this.
Yeah.
So that's kind of where we are, and this is at least one path that I can see where there are examples now where cutting the model out and replacing with the machine learning, you can get speed ups that are significant, like 2 orders of magnitude or more for some of these kind of problems. So, and that applies to other areas of physics and things.
Sure.
Where I've talked to people or listened to presentations about this. So, that's got my attention because I'm looking at 50% or something,
Yeah.
as being a really good thing if you work really hard. And that's
And probably closer to 30% if you rely on
Whatever it is.
hardware generations and things like that.
It's great if it's your retirement fund that you're improving that, but not if you're trying to get sort of orders of magnitude of speed up. So I mean, the example I use is 1 kilometer. 1 kilometer resolving clouds, a global model like that. The integration rate is sort of measured in weeks per day. And that's, let's say 1 or 2 weeks for like a large DOE system.
Really?
If you have it for a day. And okay, so, I would say that's, when you look at it practically a couple orders of magnitude below what you would need to do real weather forecasting at 1 kilometer globally, and it's probably 3 or 4, well, let's say between 3 and 4 orders of magnitude, too slow for climate. We like to get multiple years per day. Cheyenne right now, for sort of our workhorse 100-kilometer models, we can get 30 years per day out of the climate models. So that's really nice because you can run a century in 3 days of compute, of wall clock time, and then you can analyze data and do stuff.
And that's using the whole box?
No, that's not. That's actually a few thousand.
Oh, okay. So using a quarter of it or so.
Again, that's a pretty low resolution model.
100 kilometer, yeah.
Yeah, but it's still valuable for certain kinds of work.
Does the problem scale linearly? So if you went from 100 kilometers to 10 kilometers, would that be 10x more time, or is it exponential?
Oh, no, it goes at a higher power, like the cube.
Ah, okay.
So if you want to cut the resolution from 100 to 50, you're gonna, and you don't change anything about the vertical resolution of the model, just the horizontal resolution, you get a cube effect. So that would be a factor of 8 in computer resources, and your integration speed would drop by a factor of 2. So you need 4 times as many processors. They need to take twice as many time steps because the time step has to shrink as well.
Okay.
For the same amount of simulated time. And your throughput, because you have to do twice as much work basically per core, you will integrate half the speed. So if you were doing 30 years per day, now you're doing 15 years per day. If you double it again, you're doing 7 years per day. You double it again, you're doing 3 years per day. And so, and when you get to 1 kilometer, if you work it out, you find out you're doing a couple weeks per day. And at a couple weeks per day, it's climate change will have already done whatever it's going to do by the time you figure out anything with a computer running at that speed.
Gotcha.
So that, to get around that, something really different has to happen.
And that's where the deep learning might come in.
Well, it's where machine learning might come in, or some other approach that we haven't.
But something that bypasses the step of having to model everything out, brute force, simulate everything out.
Yeah, honestly, I only see 2 ways to do that. You either make the computers dramatically faster per core, or you figure out how to use machine learning to avoid having to do all the calculations. In other words, you kind of cheat. When you say, I just looked at a lot of weather and I know what it's going to do, based on this network or whatever that's been trained.
Millions of data points and run them through, and
and
makes sense to me for what it's worth.
Well, there's just a research area, and it's, I find it exciting because nobody can sit here and say it's going to work, and those are the kind of problems that you actually want to work on. You don't want to work on things that are a sure bet. Yeah. I mean, that's how you do incremental stuff, and we're clearly in a place where we need something beyond incremental stuff.
Great. Well, thank you so much for your time. I really appreciate it, and that was a great discussion.
Okay, I hope so.
Yeah. And I want to thank everybody for watching this, and we're off to our next tour stop, which is at NREL.
I got